we were looking at this image in SP34. So this image is the detailing for simply supported slabs which are one way. Okay, and the following figure in the next page. This is also for simply supported slabs, but this is for two-way slabs. And the difference that you see in both of them is, in the one-way slab you have this main bars going along only one direction. Okay, it will be arranged from this end to this end. Okay, like this. And in the other direction where you do not have the bending, there you will have distribution bars which are simply laid straight, and they'll go from this end to this end. So this side, if you view the cross section, it will look like this, and if you view this face of the cross section, it will look like this. Okay, so you people know how to view cross sections. So this is section BB shown above. So you just see so when you look at section BB, this straight line will be your distribution bar, and the dots that you see will be the main bars which are going in this direction. Conversely, when you come to section AA, which is cut across this face, you will see so in this end you will have this bent up bars like you see over here, that will be on this face, and the dots that you see are your distribution bars which are oriented along this direction. So whenever you're drawing a plan of a slab, you'll also have to know how to draw its cross section. Okay, so these are simply supported slabs, and similarly, the only difference that you'll see between a one-way slab, simply supported one-way slab which is shown here, and a simply supported two-way slab which is shown in this picture, the only difference that you'll see is when you have in section, in the other section also you will have, they will look similar. Both the directions will have the same type of bent up bars and the distribution bars. So you will have main bars in both the directions, and your distribution bars will be the function of the distribution bars will be taken by the main bars itself. Okay, so you will have this distribution bars for the purpose of holding up the bent up bars. That's it. So this is the only. So that's what you should remember. In a two-way slab, both the sides you will have the similar type of reinforcement arrangement. Okay, so this is for simply supported slabs, but what we had was a continuous slab in our problem. Okay, so for a continuous slab where you have more supports going across, so you have one support here, another support here, and similarly you may have supports for some more distance. So in such a case, this is a one-way slab. So what I have drawn over here is, basically we see here that we have two options. One is you can use bent up bars or you can use straight bars. So the easiest thing for you to do right now is to use straight bars, because when you have straight bars, if you look at our problem over here, we saw that for the negative reinforcement we required 90 mm spacing, and for the positive reinforcement at the span we required 110 mm spacing. So because of that, both the spacings are different. So therefore it is easier if we give our bars separately. Okay, a separate bar for the negative reinforcement at the top, separate bar at the bottom for positive reinforcement. So like that, if you do, you can actually do it like this, where you give the negative reinforcement over here, and then positive reinforcement you will give over here for this much at the bottom. The thing that you keep in mind is, whenever you have a support, both the positive and negative reinforcement both should start from the support or from the beam itself. Okay, so for example, this could be a wall or this could be a beam, whatever it is, it's mostly a beam if it's going to be continuous. So it should actually start from here. Okay, and it should go, the reinforcement in the slab should go into this beam or whatever type of support that it is. And you have this distance of 0.15 of L1 here represents the span of this the particular direction where you are actually giving the reinforcement. So for our one-way slab over here, we are giving our reinforcement along this direction. Okay, this is where we are giving our main reinforcement. This is 4 meters in length. Okay, this is 4 meters in length. So I have So like that I have given, I started the bar, given it for 0.4 meters from the center of this to, sorry, where's the one above. Okay, so I've given it for 0.4 meters. This corresponds to the 0.1 LX, which I have shown, which is shown over here. So according to this, you just have to provide everything that you have calculated. And in the bottom, wherever you give this kink, beyond this kink, only 1 out of 2 bars will continue beyond this point. So for example, if I have given here 8 mm bars at 110 mm spacing. Okay, so just look at this and look at this picture now. So at the bottom I have given, this is the what I calculated, 8 mm bars at 110 mm spacing. But beyond this point, beyond this particular point, I will extend only 1 out of 2 bars. Okay, beyond this point. So what is the distance? That is 0.15 times of Lx, or in this case it's 0.6 meters. So beyond this point, the spacing of the bars will be 220 center to center, and similarly on the other side. Okay, similarly on the other side also, here also it will be only 1 out of 2 bars continuing. So at the exterior support, you give this distance as 0.1 Lx at exterior supports. Interior supports, it's not 0.1 Lx, it is 0.15 Lx from the center of the support to the point where you kink it down. Okay, that is 0.15 Lx or 0.6 meters. And 1 out of 2 bars at the top have to continue for another 0.6 meters. Okay, or 0.3 times Lx, you have to continue 1 out of 2 bars. And for 0.15 Lx or 0.6 meters alone, you will have to continue every bar. Okay, so if this is, so we calculated this to be 8 at 90 center to center. Okay, so 1 out of 2 bars will be continuing past the kink, so that becomes 8 at 180 center to center. So these are our main reinforcement arrangements. Of course, this is a one-way slab, so in the transverse direction you will have only your distribution bars. So those distribution bars we calculated yesterday as 204 millimeter square per meter. That corresponds to about, we can give 8 at 250 centers. So since I'm giving it in the cross section, that distribution bars will be transversed to us or into the way, in the direction in which you are looking. So therefore they will appear as dots, and that I have marked as 8 diameter at 250 centers. And then so similarly on the top as well. One thing you should remember is, within the support, don't bring the distribution bars. Okay, so this region where the support is, you should not put distribution bars there. Okay, so that's why I marked the star and said do not give distribution bars here. So this is if you use straight bars corresponding to the, similar to the picture which is shown over here. So your task is, since we didn't have time to draw it yesterday, I have drawn it and I shared it in the teams. So what you should do after today's classes, you should look at the image which is shared and then look at this picture in SP34 and see. That will help you understand how I actually drew that cross section for the slab. Okay, so this is using straight bars. You can also use bent up bars, where only restriction that you have if you use bent up bars is your reinforcement spacing should be multiples of one another. Okay, similar to what I specified in yesterday's class. If you have one of the reinforcements is a multiple of another reinforcement, then you can adopt this. Otherwise, it's difficult. So in this case, 8 at 110, 8 at 90. Out of this, the smaller one is 8 at 90. So if I choose to give 8 diameter bar at 90 center to center for both the positive and the negative reinforcement, then I can use this bent up technique. Okay. So in this case, what you do is, if you see all these distances will be same. So here to here will be the same 0.1 Lx. Here to here will be the same 0.15 Lx. Similarly, here to here will be the same 0.3 Lx. And this kink to this center will be the same 0.15 Lx. And bottom also, from the point of this kink to the center of this support will be 0.25 Lx. So these distances will be exactly the same whether you use straight bars or whether you use bent up bars. Okay. So now what will be done is, so you have a bar starting here, and the first bar will probably be taken like this. It will be bent down and taken till this point. Okay. The second bar will start here and end over here. So one bar coming down, bent up and going like that. Another bar just going straight, going up and going straight. So they will alternate. Okay, one bar bent up, coming down and going. Another bar just bent up and going straight. So every alternate bar, so just like how you had over here, every alternate bar alone will extend beyond 0.15 LX. Okay. Similarly here at the bottom also it's the same. So one of the bars will go here. It will start from here, get bent up, and go straight. Okay. The next bar will just go from here to here straight. So here also it becomes alternate bars are one bar is bent up, another bar is straight. So it alternates. So that's how they will actually give the reinforcement. And similarly, that's what I have marked over here. I've given a small gray color line for this bent up bar, and I showed how it actually appears. So if you look at this image, you see that this particular bar, which I've given the gray dotted line, that will be bent up and taken like this and continue to the other end. This top bar and every alternate top bar will be straight, and here every alternate top bar will go straight at the bottom as well. Okay, so this is how you have it. One going bent up straight. The next bar will be just horizontal. Next bar will again go bent up. The next bar will be horizontal. So by doing that, you have the effect such that beyond a particular point, only one out of two bars continue, and your spacing becomes double. Okay, the same concept as done for individual bars, for straight bars. Okay, so it's the same thing, no other difference. And that's one more final thing to do for a slab, which is known as corner reinforcement. So this provision is given in 9.4.6. Okay, it's known as corner reinforcement or torsional reinforcement. Whenever you have a slab which is supported on either 4 sides or 2 sides, whatever it is, whenever you have a discontinuous edge means an edge beyond which there is no more slab. Okay, so for example, if I go to this the problem which we have at hand. I just need this to refresh a bit. Okay, so if you come to our problem at hand, so we have one edge over here, okay, and another edge over here, for example. But this side is the end, and this side is also the end. So this edge is a discontinuous edge because there's no slab on this side, there's no slab on this side, there's no slab on this side. However, if you come to this place, there is no slab on this side, but however, there is a continuity of slab between here to here. So I would say that this is a corner where one of the edges is discontinuous, the other edge is continuous. Okay, so this is how this looks. And similarly, if I have a slab system where, say this is the slab system, okay, then I would say that in this place all the edges are continuous. In this place both edges are discontinuous, and this place one edge is discontinuous. So whenever you have discontinuity of the edges, you have to give torsion reinforcement. Otherwise, what will happen is when you apply a load, the corner will tend to lift up. Okay, so this is basically to prevent lifting up of the corner under a vertical load. Okay, so the corner will lift up. This is just similar to you keep a paper on your hand, press it in the middle. The edges of the paper will try to lift up a bit. So it's the same effect. So to prevent that, you have to give a torsion reinforcement or corner reinforcement to keep the slab down. So how do you give that? So this is mentioned over here in 9.4.6. Torsion reinforcement shall be provided at any corner where the slab is simply supported on both edges, meeting at the corner, and is prevented from lifting. Okay, and unless the consequences of cracking may be, it consists of top and bottom reinforcement, each with a layer of bars placed parallel to both the sides of the slab and extending from the edges to a minimum distance of 1/5 of the shorter span. Okay, distance is 1/5 of the shorter span, 1/5 Lx. The reinforcement per unit width on these layers shall be equal to 3/4 of the area required for the maximum midspan moment per unit width. Okay, so what is the midspan moment maximum that we found for that particular panel? Okay, so 3/4 of that you have to give as corner reinforcement. Okay, in case one of the edges is continuous, then you give half of it. Okay, 3/8 of the, or in other words, 3/8 of the positive reinforcement. So these details are given in the next picture, not this one, this one. Okay, so if you have a discontinuous edge, you have to give a mesh like this. Okay, so the total reinforcement going in the x direction should be equal to 3/4 of what is that? 3/4 of the maximum midspan moment reinforcement. Okay, so that is what is actually mentioned over here. Okay. Okay, so that much you have to give, and similarly you have to give 3/4 at the top, 3/4 at the bottom. Similarly, 3/4 at the top and bottom in the vertical direction as well. And how much will be the distance of size of this mesh is Lx/5 and Lx/5. If you have an edge where you have only one side is discontinuous, the other side is continuous, then you take half of it. Instead of 3/4, you give 3/8, and the spacing of the mesh becomes bigger. So that's what I have drawn as the third image. Okay, so I calculated my positive reinforcement is 482 mm² per meter. So let me say it's 500. So 3/4 of 500, or you can give it as 482 also. So 3/4 of AST positive, which is 3/4 of 500, is 375 mm². So you have to you may use 8 mm bar or something, or 6 mm bar if you want to make it smaller. The total area of that bar on the top and bottom in both the directions, you give it such a spacing that it comes as 375 mm² over a distance of Lx/5 or 4 meters by 5, which is 0.8 meters. So that is the size which should be given. So 375 mm² top and bottom in both the x and y directions. Similarly, this corner as well. This corner is only one edge discontinuous, so therefore you give 3/8 of it, or approximately it comes 187.5, so about 200 mm². Okay, top and bottom in both these directions. So 0.8 plus 0.8 is 1.6, and this height is 0.8. Okay, so these are the images which I wanted to show you. Please have a look at the 3 drawings which were shown to you, and also have a look at this section on slab reinforcement. Okay, so have a look at all of this. Okay, so this is something that you have to study on your own. I cannot show everything. It will take a lot of time if I have to cover a very bit of detailing. Okay, so similarly also have a look at other parts of this code book which you have studied till now. For example, beams. If you go to page number 97, beams, maybe 107. Okay, you go to beams, have a look at how you can, it gives you all the details of how to actually arrange bars in your beam, minimum clearance between individual bars. It gives all the reinforcement details, minimum tension reinforcement 0.85 dd by Fy, all the things which you have already seen. Okay, so if sometimes in rare cases somebody may want to give a group of bars instead of single bars. So in case you're doing like that, what you should do? Okay, so all these details. This is all special cases. You need not pay too much attention to it. Just look at the things which you would normally use. Okay, so reinforcement spacing rules, like this is there in IS 4 physics also, this table. So similarly, compression reinforcement, minimum percentage, side face reinforcement. Shear reinforcement, we have not studied shear yet, but when we come to it, you'll know. There is something known as stirrups, how to bend the stirrups, how to hook it. All these things will be shown to you. Okay. It's a very good code book to have a look at. And similarly, so later after you finish studying shear detailing also, then you will know that in a beam you will have longitudinal reinforcement, you will have shear reinforcement or stirrups. So when you give both of them together, how do I draw the longitudinal section of the beam? Okay, this typical arrangement of bent up bars and vertical stirrups in a continuous beam. Okay, so yeah, so this is the thing. So have a look at this code, have a copy of this code book with you. So what I'll do now is I'll just start for a few minutes shear, and then I will be closing the class because I have some other meeting to attend. Okay, so now shear design of RCC beams. Till now, you have been seeing simply supported beams, continuous beams. You've been designing them as under reinforced beam or over reinforced beam, T beam, whatever they are. Okay. So based on what condition criteria did you actually decide the depth of the beam, reinforcement, and all those things? What did you use to decide it? Decide the reinforcement and depth and all? Based on what force?
Flexural force.
In other words,
Bending.
yeah, you've been only looking at the bending moment in a RCC beam. So as you know, you study the mechanics of solids. You know a beam does not have only bending moment. What is the other diagram that you draw when you are given a beam? One is bending moment diagram. The other one is
shear force.
Shear force diagram. So most of the beams will have a good amount of shear force, and they need to be designed for it. Okay. Otherwise, you may even if you make your beam very safe in flexure, if you do not, if you forget to look at its shear force resistance or condition, you may. And by the way, shear force failure is much more dangerous than flexural failure, because at least for flexure you can give under reinforced design and you'll see yielding and all those things. I mean, you know the benefits, the reasons for giving under reinforced design, no? So all those things will be there. But if a beam fails in shear, it will be sudden. Okay, and there is not much you can do about it. So shear design in a way is much less, it's much more worrisome than flexure failure. Okay, so this is a simply supported beam. I hope that you know this is how the shear force diagram will look. Okay, and obviously shear forces will be maximum at the support equal to the reaction value, and at the middle, if you have a unit, it will be 0. And this is how a beam will fail under shear. Okay. So what is the difference between this and the way the cracks will come if the failure is from flexure? How will the cracks appear if the failure is mainly from flexure? Where will the cracks be?
It will be in the bottom perpendicular approximately.
Okay, at which location? Where along the beam? Along the length where?
Middle span.
Middle span. So basically these cracks that you see, the mild cracks, these are all flexural cracks. But this cracks haven't opened up or broken the beam entirely. However, you see a crack coming from the support, not going straight, it's going at an angle, about 60 degrees or something. Okay. So these cracks are shear cracks. Okay, they have happened because of shear, and that is why they are occurring at the support. Okay, because you're having your high shear force at the support. And you see that this failure, no, it's not as easy to arrest as flexural failure. Okay, and it is much more. It's of worse consequences than a flexural failure. So this is a failed beam with flexural cracks and shear cracks are visible. Maximum shear stress is at the points of concentrated loads or reactions. So this point, this point, this point, and this point. These are the locations of your maximum shear force. Okay. So you know bending stresses. Okay, so whenever you have a bending moment at a particular section, you do my by I, you get the bending stress. Has anyone come across this formula for shear stress? I'm not sure whether you have come across, that's why I'm asking. Have you come across the formula for shear stress? Shear stress distribution across the depth, I mean. Have you come across this one? Okay, this one, are you people familiar how this comes? The flexural stress distribution. This you are familiar, right? This double triangle. Yes, sir.
Yes, sir.
Okay, fine. So this is flexural stress distribution across the depth of a beam. This shape or parabola kind of thing that you see, it is the shear stress distribution across the depth of a beam for a given shear force. Okay, so this basically tells you two things converse to both of this. Flexural stress, you see it's maximum at the top and bottom. Shear stress distribution, if you see across the depth, top and bottom at the surface of the beams, you will not have shear stress. Rather, your shear stress will be maximum where your neutral axis exists, or your flexural stress is 0, there shear force is maximum. What do you think is the reason for this? In terms of bending moment and shear force, do you find any similarity? Have you seen the similar relation between shear force and bending moment? In general, where will bending moment be maximum?
At the bottom.
No, not like that. I'm asking like you're having a beam. It's having a very random set of loads. Okay, and you're writing the bending moment equation, and you get a bending moment equation. You are asked to find. Like where the shear force is. You want to find the location where shear force is maximum. What will you do? You have an equation for shear force, you have an equation for bending moment. You have been asked where is the shear force maximum. How will you find the location? You have both the equations, bending moment equation and shear force equation.
So differentiate it and get the value.
Okay, so differentiate.
The maximum shear force, the bending moment is 0.
Exactly. So where the location your bending moment is 0, that will be the location where your shear force is an extreme. So that is what is almost similar over here. Your shear stress is 0 at the neutral axis. Shear stress is maximum. Okay, and this is how it will look. It's a parabola. So there are different. There's the concept called as shear flow. Okay, and things like that. It's a big derivation to find this. So the formula is tau equals VQ by IB. V is the shear force. Q is the first moment of area up to the particular location where you are finding the shear stress. I is moment of inertia, and B is the thickness for the. So for this beam, this is I, this is B. Okay, the width of the beam, thickness or breadth, that is B. So anyway, just know that there's such a formula which exists. Unfortunately for you in your syllabus, it's not there anywhere. Actually, it's a pretty important topic actually. So anyway, I think I'll have to stop with this. So just I wanted to give an introduction to why shear force needs to be designed for, how it and what is the reason and how this actually manifests. So this is what I wanted to cover. So I'll stop with this. I have to leave. And by the way, your midterm test will be on 20th. Okay, which is the Wednesday next to coming Wednesday. Okay, that is when your midterm test will be. Most probably, I will be trying to keep it in the class hour itself, 9:30. And what is your 10:30 class on Wednesday? Wednesday 10:30. What is the class that you have?
So environmental engineering.
Environmental. Okay, who is taking for your section?
So Gandhimathi ma'am.
Okay, I'll ask her if she's allowing me to actually take her hour, and I'll give her the next day my hour also. Okay, so that she can take compensation. If she allows me,
So for B section, it's Swaminathan sir.
Oh, yeah, both of them. Okay, I'll just ask them, and I'll tell them I'll give them another hour, whichever they want. So I'll keep it from 9:30 to 11:20. By 11:20 you have to stop writing. By 11:30 the exam will close and no answers will be accepted. Okay. So that's what I wanted to inform. Okay, so I leave now. I'll see you guys again on Wednesday. Okay. Okay, but I'll close the meeting. I have to go. Okay, bye.